All right, so we'll go ahead and get started. So last class I started asking you guys a little bit about sort of whether you guys have discussed at all HOMO and LUMO, which apparently you guys haven't really discussed that much. And we were discussing it within the context of sort of 1,4 addition. So again, the idea is if you take a molecule like acrolein, there's a couple different ways that you can add into acrolein, as we discussed, that are in one way based upon, you can sort of think about electronic effects. So if you have what we often call a hard nucleophile, so something that's generally a little bit more charged, things like alkylithium, you will get, for example, methyl lithium, right? You will get what we call 1,2 addition. Where we left off, though, was this sort of idea of a 1,4 addition. So this is 1,2. This is what we would call 1,4, and there's a variety of different nucleophiles that will react in the 1,4 sense. In fact, it's probably even more common. So, for example, Gilman reagents and cuprates, for example, when you take these guys and you treat them with a molecule like acrolein, in these cases, what's going to happen is you're going to actually get sort of 1,4 addition. So the way that we can think about this, again, I'll just leave out everything else for make it easier and just sort of treat it as a methyl nucleophile. The addition is going to be into the alkene, and we're going to push the electrons through the alkene up into the carbonyl. Again, early on, what you need to do is take this molecule and draw, for example, the resonance form that we discussed. You can certainly do that. In this case, what you have, right, is you have your acrolein. So again, it's 1, 2, 3, and then the oxygen. You have sort of a negative charge up here. And again, once we quench this reaction, the net product that we're going to generate is going to be carbonyl, right? Because we'll protonate it, and then we'll go from the enol to the keto form, or in this case, the aldehyde form. And up again, up above, in the 1,2 sense, we're going to get that sort of methyl alcohol, right? So the sort of reason why these reactions take place, again, you may be able to understand the electronic effect of 1,2 addition. At least that's one way you can think about it. Again, we sort of call it hard-hard interaction. So when you have a very charged nucleophile, something like methyl lithium, where we have very tight negative charge character to that nucleophile, it's going to be attracted to where the strongest positive charge is on the electrophile here. And it turns out that happens to be this carbon here. And again, you could reason this based upon the proximity to the oxygen and the fact that you have a sort of polarized bond there. The other reaction, sort of going through in my head this morning, how I would sort of explain this to you guys in a way that hopefully makes sense based upon what you've seen. And I think the issue is that the real reason why this forms, and sort of discussing HOMO-LUMO interactions, may be a little bit tricky. And we're going to get into HOMO-LUMO interactions a little bit more within conjugated systems. So we'll learn about Diels-Alder, and so we'll learn about HOMO-LUMO interactions in terms of allowed processes and unallowed processes. And so what I decided, one way that instead we could reason this transformation from, rather than just sort of accepting, right? Say, oh yeah, this is where the where the LUMO orbital is the strongest. Like, what does that mean to you guys, right? At this point, nothing. And to me, it doesn't really mean that much either, in part because these values, these HOMO and LUMO interactions, and the energetics behind them are often calculated using sort of complex math that certainly goes beyond the sake of this course. But we have seen regioselectivity in a bunch of other cases, right? And perhaps the better parallel in a way to draw here maybe to draw a parallel with sort of kinetic and thermodynamic control in a way. If we imagine addition, right, being driven by charge, hopefully you guys could probably reason that, and that can make sense. But if what I told you, instead of saying, oh, it's the LUMO, if maybe what I told you instead was to say that usually you want to add in this bottom way, and the reason is because it's thermodynamically favored. Now, looking at these two products, could you guys come up with a reason why the bottom molecule might be thermodynamically favored over the top? Based upon a trend that we've seen a lot. What was it? You were saying something. I'm hearing something, yeah. So in this case, we still have our carbon-oxygen double bond when the product is formed. In this case, we don't. And so to sort of at least rationalize this, given your guys' current understanding of organic chemistry, and to sort of perhaps add and advance something we've seen in the past, maybe the best way for us to reason this is to consider, instead of going into the sort of real molecular frontier orbital theory explanation behind it, is to just sort of think about it being a thermodynamically controlled process, right? At the end of the day, what we have is a product that has a carbonyl. Again, I understand that there's some inconsistencies there, but at least that's something that you guys could reason, and at least you could sort of, that's certainly based upon factors that you guys know. We've seen time and time again that carbonyls are really good and strong bonds that we could have, and so by adding 1,4, we preserve the integrity of that carbonyl, and so that could be something that we would like. And so I think perhaps this is the way for us to think about it, and certainly for the majority of this course, it's really this 1,4 addition that we're going to see a lot. Usually that's it's usually the one that sort of, I shouldn't say usually, but you see that a lot. It's very common for 1,4 additions to take place, and 1,2 additions it's only when you have very highly charged nucleophiles. Okay, so here's 1,4 versus 1,2. Does that make sense? At least can you guys rationalize that? Okay, so moving on to enolate chemistry, one of the perhaps most common and certainly one of the early 1,4 additions actually span from enolates. And so as we sort of discussed, and let's just sort of add on to this concept, methylithium, right, is a very highly charged species. The negative charge of methylithium is localized onto a specific carbon. That means it's very dense and negatively charged at that position. If instead our nucleophile is an enolate, it is also, and can be, say for example, a lithium enolate, right, which is what we would form with LDA. So you might look at these on the surface and say, well, now we have another lithium-bearing nucleophile. Sorry, with the lithium counterion, but it's the same kind of concept here, right? It's a carbon-based nucleophile. It's got lithium as a counterion, so it's similarly, you might imagine it's similarly net charged here. But what's the one big difference, as we've discussed, between an enolate and methylithium? We have this resonance. So in fact, that negative charge is really spread out throughout the system, and so an enolate, in this case, is actually a much softer nucleophile than perhaps methylithium. And so it turns out that when you make enolates, you will actually do a 1,4 addition. And again, this is one of the early 1,4 additions. We're going to have a lot of carbons here, so you got to make sure that you don't add or drop a carbon here, so be very careful. Right, we're going to make this bond here, and then we have our 1,4. Right, so we get our 1,4 addition into that acronym. So I just sort of made it blue so you guys can see, and then this is the bond that we're forming. And the net result is that we get these diketones. Let's use. 1, 2, 3. And once we sort of quench it, right, with a water source of some type, this is what we get. And so, again, once we start branching out, it's oftentimes a good idea to check the number of carbons that you have here, right? Conservation of mass, conservation of charge. So you've got your R and 2 carbons, R and 2 carbons, right? And then the question is, do we have our acrolein, which is 1, 2, 3 carbons and an oxygen. So 1, 2, 3 carbons and the oxygen. Okay. So this is the product of enolates adding 4. I've just shown it with acrolein. This is very common with a variety of alpha-beta unsaturated systems, such as this. And it's one of these reactions that has a name, and the name for it is, in fact, a Michael addition. Okay? This is just one of the people that found this reaction and studied this reaction, and so the name is after them. Now, what you find, in fact, in the literature is that this is a Michael addition, and by virtue of this being one of the first examples of a 1,4 addition, almost every other addition 1,4 basically sort of in one way or another bears that name. So what ends up happening very frequently in the synthetic chemistry community, even though it's not necessarily 100% accurate, is that people will refer to any 1,4 addition as a Michael addition. So if you say we Michael it in, that's often the sort of verb, right? It's like we Michael it into the system. And so things like oxy-Michaels will be 1,4, but even if it's just other nucleophiles, people will call it a Michael addition, even though it's technically not a Michael addition. So, yeah.
For the product, that's a keto-enol reaction, right?
Yeah, so you're just going to protonate.
Okay.
You're going to generate the enol, and then it's going to go to the sort of aldehyde. Okay, so enolate chemistry is some of the early work that we've seen, and so now we've learned the Michael addition. We have a quiz coming up, and I want you guys to know mechanisms. And I think one fairly good mechanism type question that's fairly involved and has actually been very, very important for synthetic organic chemists that involves enolate chemistry is a reaction that Robert Robinson sort of developed way back in the early, at this point almost 100 years ago, which is called the Robinson annulation. Just want to make sure I don't miss anything here. Okay, so the Robinson annulation Robinson annulation is effectively a two-step process. Again, I'm just going to show one example, but in general, what a Robinson annulation is it's a Michael addition followed by an aldol condensation. So I'm going to put up an example of a Robinson annulation. I'd like you guys to all sort of go through this mechanism with me so that we can revisit Michael additions as well as aldol condensations and try to come up with the answer to this reaction. And oftentimes this is actually carried out under acidic conditions in a single step. But to sort of stay consistent with the enolate chemistry that we've been seeing, we will treat this as a enolate-driven process, and then at the end we'll treat it with a mild acid. Okay. So, sort of first step in this reaction is we're going to take this and treat it with, let's say, LDA, which again is the base lithium diisopropyl amide. And then what we're going to do is we're going to trap this with methyl vinyl ketone. Okay. And first step in this reaction could be a Michael addition in the system, so we should probably think about how that's going to form in this case. And then the second step will be to effectively allow the reaction to continue to go, and then towards the end we'll treat it with a mild acid. So I'll just say sort of hot mild acid. And heat, and in this case what we'll facilitate is the end. We won't really need this one until really the end, and this will be the condensation part of the alcohol condensation. Okay. And so the product that we're going to generate is going to look something like that. So we basically done an annulation, so it's called the Robinson annulation. Bless you. There's a cold going around. I definitely have it. But this is a Robinson annulation. The annulation is just a way to sort of say ring forming process. So you can sort of see we're forming a ring in this process. So here, question? All right, so let's go through this mechanism and think about how this sort of happens together. Okay. The first sort of step in this reaction should be fairly obvious. When you have this mixture of methyl vinyl ketone as well as this 1,2-diketone in the presence of LDA, what is going to be the first proton and first enolate that you guys think we're probably going to form? Yeah?
The one in the ring, because it's stabilized by 2.
Exactly. Right? So we have a 1,3-diketone on one case, and in the other case we just have our standard enolate. So even though we have a really strong base, which could in principle deprotonate here, and we will probably do that later on in the reaction, what we will do instead is the first step will be to deprotonate this hydrogen here, because that's going to be the most acidic proton in there, right? You can even deprotonate it using to even deprotonate it using a much more mild base than LDA. Okay, so we generate our enolate. And I basically told you guys what the first step's going to be, so what do I want to do at this point now? What's that? We want to do the Michael addition, so tell me how we're going to push those electrons. So you guys should try to draw this before I draw it. All right, we're going to sort of do a Michael addition between these two. Go ahead and see if you can push those electrons in the right way. Give you guys a few seconds, and you can see if you're right. All right, so we have it up in the enolate, but there's going to be a lot of arrows being pushed here. Right? And you could draw the resonance form if you really want, but we're just going to go straight to that carbon. Right? And this is just a case where you have to keep pushing arrows, right? Because if we stopped here, what's going to be the problem? 5 bonds to that carbon. Right? So I got to keep going. What would be the problem if I stop there? 5 bonds to carbon again. Right? So we got to keep going, and so we got to keep pushing these electrons, and eventually we get up to that oxygen. How are we doing now? Good, I see some thumbs up. Good. Okay, so this is the Michael addition. Okay, so that's the Michael addition, and in fact, again, we have that enolate. For the sake of board space, I'll just sort of leave it there for a moment. But sort of recognize that once we're here, we can eventually all keto form. But what really needs to happen here is the last step of this reaction is sort of what? Or the next phase of this reaction. Right? We've now made the first carbon-carbon bond. In this system, again, here's the methyl. And that methyl is going to be that one right there. And so again, these molecules might not look that same, but we're getting very, very close to being able to actually get to the product. Yeah. Okay, so I think what's being said here is that we have here an aldol condensation product. And so what was suggested was that the enolate is now going to attack this carbon. Is this the enolate that we want, though? Let's look at this bond size that we have, right? This ring system is a 6-membered ring, right? 1, 2, 3, 4, 5, 6. 6. 1, 2, 3. So that would be only a 4-membered ring. Where's the 6th? Yeah, it's on the other side. So what do we need to do before we... So you're right that an enolate has to do a 1,4 addition, but it's not that enolate. What's the enolate that we want? The other enolate. So what's the what do we have to do here? You know, we usually see it with we saw it a lot. This, I would just draw it, even though it's not likely taking place in termomolecularly. We just draw it for board space. Right? Proton transfer, right? So we usually see it with heteroatoms, but the proton transfer that we'll do here will actually be that proton. And we'll switch the place where that enolate is. And now we've got the enolate at the appropriate place. I recognize there's a bunch of arrows there. I sort of urge you guys, for the sake of time and board space, sort of leave that there. I urge you guys to try to make sure that you can see that. If you need to, go ahead and use, say for example, the conjugate base of LDA, the conjugate acid of LDA, the protonate it, regenerating LDA, and then deprotonating it if you can't see it in this way. So again, this is almost certainly not what's happening. This is just a proton transfer that we're going to show for the sake of board space. Okay. Now we've got the 1, 2, 3, 4, 5, 6, right? So what's going to happen here, and sometimes in organic chemistry, being able to see things a little better, oftentimes it's helpful to sort of redraw the molecule, and I think what might make it difficult to see what's going on here is that the group is way over here, right? And the carbonyl that we want is over here. Maybe, right? We could look at it that way. But this is a symmetric molecule, right? Everybody sees the plane of symmetry there. So it really doesn't matter which carbonyl we attack, it's going to lead to the same product. So instead of trying to draw, we either could redraw this so that it's up there, or we'll just sort of recognize that this is symmetric and realize that we can form this 6-membered ring, or we could just form this 6-membered ring. And because it's just for our own visual, it might just be easier to just make this 6-membered ring down here. Okay, that's going to get us to okay, so again, it's oftentimes difficult when we're dealing with rings to see exactly what's going on, so sometimes you can just count, right? So let's look back at the previous counting that we did. So this would be 4 down here, right? So we have, now this is going to be 6, right? This will be 1, 2, 3, 4, 5 here, right? So this will be 5, and we're making a bond between 5 carbon and 6 carbon, right? And we have 1, 2, 3, and then the carbonyl is at 4. Now these two molecules are now looking very similar to one another. The challenge of seeing this, again, comes back to sometimes having to redraw these molecules and seeing it in perspective, right? So these might not look the same per se, but this molecule flipped over that way. If we flip this molecule in the plane of the board, basically 180 degrees, right? Now the carbonyl is going to be going down, the methyl group will be going down, right? And the difference will be is that we'll have the carbonyl up there. We won't have that double bond, but we'll have the oxygen at that position. Everybody see that? And so what's the final sequence of steps that we need to do to get there? We're going to treat it, for example, maybe propionate or something like that, but that sort of second step where we do the mild acid and a little bit of heat, that's where the elimination is going to take place. Okay, so make sure that you can do that. So again, we'll protonate this. Under mildly acidic conditions, we can generate water as a leaving group and simply do the elimination, and that's how we're going to get there. Okay, so this is a sort of a Robinson annulation, and definitely be prepared for this and this level of question for the quiz. So you guys should all be able to draw this for the upcoming quiz. The reason why I showed this specific Robinson annulation is that what you've noticed is that you have this 6-6 ring system, and we're not going to get too much to it today, or we're not going to get too much this semester, but in really a lot of biological settings, let's see if I bring this up. There are a lot of compounds that are sort of terpene-derived compounds that people have used this starting material to sort of synthesize. So I'll show a few. And then I'll make a point because I'll sort of transition very briefly to sort of enamine chemistry. So for example, steroids. It's not the images I wanted. It's not chemists. Steroids, structure. So for example, here's what's sterol. This is testosterone, for example, right? So you see testosterone, it has sort of this 6-6 ring system, right? And then you actually have a methyl group at that position, similar to what I had shown before. See some of the other ones that you have here. So we're mostly showing testosterone, but like estrogen, for example. Right? Estrogen has a benzene group at that position, but again, it's a 6-membered ring. You can imagine aromatizing it, right? So again, a 6-6 ring system. Turns out that oxygen is where you could bring the carbonyl group, for example. But again, hopefully the sort of points become clear. In addition, there's a lot of what have been really important natural products that are derived of these. When I was a graduate student, I was working on this molecule. This is a natural product that I worked on, and that's actually mine. So again, this is a natural product called checospongonolide, for example, just to give an example of what I work with. I know the structure is kind of small, but you again see the sort of 6-6 ring system there. So lots and lots and lots of different targets that are sort of made from these, and that you can imagine these molecules would all, well, not in the case of estradiol, but a lot of them have stereochemistry, and the stereochemistry becomes very important in terms of setting that stereochemistry. So the Robinson annulation was really important, and specifically kind of the one that I've shown here was really important because this scaffold here could serve as a building block for a lot of those molecules that we described. So we've got functionality here which we could use to modify. We've got functionality here that you could use to modify. You could bring in a methyl group here. If you wanted the methyl group, for example, there instead, you could have a methyl group at that position. So there's a lot of flexibility to make sort of what we call Declan scaffolds. You can even make, for example, 6-5 systems as well. If, say, for example, this was a 5-membered ring and you want to make that part of the steroid. So it's a very, very useful a reaction, and very important reaction. But taking this one step further, all those molecules that I sort of showed you, they were all chiral, right? And as you guys discussed last year, right, you have, we're all chiral, and so especially when you're looking at a molecule, say for example for therapeutic importance, the difference between the two enantiomers can have different, say for example, physiological effects. And so if there's, say for example, a target that was isolated and it had potential as a drug, one enantiomer might work really well, and the other enantiomer might not work at all, or in the case of things like various drugs, you could perhaps get side effects. And so it's very important to be able to make them as a specific enantiomer. Okay. Now, what's interesting about this reaction, right, is that you have this, we just discussed it before, right? We have this symmetry that's here, okay? And we didn't really imply any stereochemistry to this molecule, but if I did show stereochemistry here, this molecule is achiral, right? There is no chirality in this structure. However, the moment that this reacts with this molecule here, right, now we've got something that's actually chiral, right? And what's also interesting, right, is that it could have reacted with either one of these, right? We just chose to react with this carbonyl, and it happened to lead to this enantiomer. But if we reacted with the other carbonyl, we would get the other enantiomer. And so these carbonyls are what we call sort of prochiral. When you modify one of them over the other one, you suddenly generate a stereocenter. Okay, so question becomes, how might you differentiate adding to one carbonyl over the other? And if you could do that, you might be able to generate enantiomerically pure versions of this, and you could perhaps make one enantiomer or make the other enantiomer, and those could be valuable building blocks for a variety of different targets. So we'll come back to this in a second, but I will leave that up right there. I'll leave all that other stuff. Okay. So in the book, the book discusses, we've been primarily to date discussing enolates, right, as ways to make really good nucleophiles, right? So if you take a ketone and you treat it with LDA, you can generate enolates, which are then very good nucleophiles to add and react with electrophiles. But there's another way that you can activate carbonyls or enolate-like reactions. And in a way, we've seen this in the past, sort of reiterated here, and that's to make enamines. Okay, so this is from the carbonyl chemistry chapter, at least the condensation part of it. You guys should all be able to draw this mechanism and recognize that if you have a secondary amine, and that secondary amine condenses with onto a carbonyl, what you get to is that sort of enamine. And so once you have the enamine, there's really two factors of this that make it good sort of good enolate-like properties, right? So we've effectively locked, so the first thing is by making the enamine, we've effectively locked it into that kind of enol form, right? It's not going to be able to, you're not going to have some tautomeric version of this, right? The R group on that nitrogen isn't suddenly going to jump over here. So we've locked it into what is kind of like an enol, right? To the same extent, we've given it actually even a better donor into the system because a nitrogen is better at stabilizing positive charge than oxygen. And so enamines are very, very good at reacting through processes such as aldol reactions. So you can basically use enamines to generate this type of system. Okay? When you do this, a few steps. Right, you can imagine getting to a system like this, right? After we sort of do this and protonate it. But now we have the iminium, which we can either go back to the enol form, we can either go back to the enamine form, or what we can do is hydrolyze this and basically get to the same product that we showed before. So in the presence of, say, for example, an equivalent of water, even just one equivalent, you will hydrolyze that and you will get to effectively the aldol product. So the book discusses enamine chemistry in terms of this activation, and it discusses it in terms of under acidic conditions, and it discusses how it can actually be a little bit softer, so it might be less prone to do things like elimination chemistry, background acid-base chemistry. What I'd like to show you guys instead of that is something that I think is really cool about enamine chemistry, and that's the ability to use secondary amines to catalyze enolate-like processes. So some of the most important chemical transformations that are developed among synthetic organic chemists are those where you catalyze a reaction, and in that way you're able to generate a specific enantiomer. Okay? And as it turns out, perhaps a very famous way to do this, and one way that's been known for a long time, and within the context of the Robinson annulations is in fact one of the first ways, is to use as your here, let's do a catalytic cycle, is to use a chiral secondary amine. And they actually use primary amines can be used for this as well, but what's largely used is a secondary amine they just tend to work better. But in this process, what we're going to do is you could imagine that, just take a quick step back, if instead of having an enolate here, if this was an enamine, right? You should still be able to do that condensation process based upon what I just told you. But the added benefit of having an enamine here is that what if those two R groups actually had chirality to them, right? For example, proline. Right, where now we have a stereocenter on this molecule. Now the condensations, the actual reaction itself is not an enantiospecific reaction. It's what kind of reaction? It's not enantioselective, it's what? Diastereoselective. And you can certainly do diastereoselective processes, right? So now, after we do the condensation, for example, right, you have a stereocenter here. Again, we'll have a stereocenter there that'll eliminate, but you also have this stereocenter here, and so it's these two. Okay? And so if this is always set, if this is always the exact same stereoisomer, whether it's R or S, whether this is R or whether this is S, now those become diastereomers of one another, and so you can have a diastereoselective process. And there's transition states. I'm not going to go through all the transition states for this, but let's just say that you can imagine hydrogen bond, directing here in sort of a chiral environment. There's a bunch of different proposals for how this induces that diastereoselectivity, but you can sort of see that overall process. And so proline is used quite frequently, and a variety of different proline-based catalysts are sort of used to catalyze enolate-like reactions. Okay? So how this would work, right, in terms of a catalytic cycle, right, is that you would have, say, for example, your we'll just do it for a standard aldol reaction, for example, right? You would first condense. Generate your enamine. So that would be the first step, right? Then what ends up happening is you have your second guy, say for example, an aldehyde. Right? The aldehyde will then react with this through an aldol reaction. Through this process, right, we're generating again, I'll show the protonation as well, so you guys should be able to see this. But what's happening here is now we're generating a stereocenter. So this overall complex has two stereoisomers. This is set because we basically bought proline, which is a single enantiomer, and we know which one it is. So when the transformation takes place, it ends up being a diastereoselective process, which is okay. I don't know exactly what the real stereochemistry here is, but it's set. Let's just say that it's set. Then what ends up happening is, right, in the presence of water, maybe you have a couple equivalents of water in this reaction. You're now going to hydrolyze this system, regenerate the proline, and get an aldol product that's now a single enantiomer. Does that make sense? Right? And so in this way, you sort of recycle this. It keeps going through the process. Generally, people are able to get away with really low amounts of these. It's fairly common to use 20 mole%, for example. So each proline, in this case, would cycle through 5 times, for example. But it's not uncommon for people to be able to get down to, say, for example, 1% catalyst or 0.1% catalyst. And in that case, each unit is going through 100 or 1,000 different cycles of this transformation. And so what you're able to do is take a stockpile, right, chiral molecule, which we can get. It's a simple amino acid, and we can get it. We can actually get the unnatural one as well if we want. It's a little bit more pricey, as you might imagine, but you can sort of take biological compounds that we have that nature gives us, and we can use them through processes such as this to generate a new chiral compound that might be unnatural, but then we could use that to generate other valuable chiral molecules. And so this is usually where I like to discuss sort of enamine chemistry, because I think this is a lot more interesting. And again, within the context of the Robinson annulation reaction, all those steroids, for example, we talked about, was in fact one of the very, very first examples of what we call sort of organocatalysis or asymmetric organocatalysis. So using not metals, but sort of non-metal based carbon sort of catalyst to do this transformation. So this was known back in this reaction was, I think, developed back in like the 70s. Robinson annulation came about back in like 1920 or so, maybe even before that, I forget the exact date. The proline-derived version or the amino acid-derived version came about in probably about the 1970s or so. And at around the time that I started grad school, at around 2002 or so, people were really starting to go to town on new ways to do this type of chemistry and other transformations. So it took a little while to get to that step, but then it really just exploded, and people have been using sort of chiral enamine catalysis to make a whole bunch of different starting materials and new chiral reagents. And this is actually Stacy Brenner, for example, that you guys know used to be here. She works on a lot of chemistry involving this as well. Okay, so that's really all I want to talk about. That's how I just want to introduce enamine chemistry because I think it's a little bit more interesting. Okay. All right. All right. How many more reactions do we? Yeah.
So when we have a problem like that, we write for the answer like 1 enantiomer, right? As opposed to
So the question is, yeah, I mean, recognize that it's a chiral reaction and you could generate a single name, right? I don't know. I mean, I could ask a question. I could ask a question like, just generally explain why proline can lead to a single enantiomer or something like that. And the sort of idea would be it's a diastereo. You generate a molecule that already has a set stereocenter, and thus the reaction becomes diastereoselective rather than anti-selective or something like that. I don't know. Again, you should be able to draw a mechanism for enamine chemistry. So if you sort of have even just a more generic one, you should sort of get that generating the enamine can then lead to a new nucleophile, like the mechanisms of that and stuff like that. But, all right. So we've got a few more. We've got about another half hour. I've got a couple more reactions to discuss. Actually, it looks like I just have one more, and then I'll discuss a quick spin-off to sort of show you guys that what we've learned the last couple of days could certainly expand into other avenues. Yeah.
You just give us like one of those practice problems for this type of chemistry.
Yeah, if I have time. Let me just get through the rest of the chapter. The next two reactions that I want to discuss are two reactions that are basically the same reaction, but one is an intermolecular reaction, one's an intramolecular reaction. And these are the Claisen condensation and the Claisen condensation is going to be an intermolecular, and a Dieckmann condensation this is for intramolecular. So just whether or not this transformation takes place to form a ring, for example, in intramolecular context, or whether it's two reactions taking place together. Okay. So what differentiates Claisen and Dieckmann condensations from what we've seen to date is, we've seen aldol chemistry where we take a enolate, or in the case that we just saw, an enamine, and treat it with an aldol, or an aldehyde, and we sort of add in, and we can do the aldol condensation. So that's one example of enolate reacting with a carbonyl. We've seen a Michael, which is an example of an enolate reacting 1,4 into an alpha-beta unsaturated carbonyl. But the Claisen and Dieckmann is a reaction whereby the enolate that we generate actually reacts with an ester. So I'll just say OR. We'll just make this R1 and R2. And so it turns out that enolates can react with esters. But as you sort of might imagine, based upon what we've seen in the past of adding molecules into esters, is that once we do the addition, so once we do that first addition, what do you guys think is going to happen? So you add into an ester, you generate the enolate. What's going to happen at this point? So we add in, go up here, and come back down. We're going to kick off ester. And so we generate 1,3-diketones. Okay, based upon what you guys learned previously, what might you suspect could happen now? Maybe add it again. But that doesn't happen. And the reason is that this isn't your standard ketone that we're now generating, even though these might on the surface appear to be more likely to react. This is a 1,3-diketone, right? And so this 1,3-diketone is very, very different than our normal ketones, right? And why is that? What did we discuss about these 1,3-diketones? Yeah. Say again? It's got a very acidic proton. It's one way that we could look at it. But we also know that in this sort of form that we have drawn here, it's not even really how it exists, right? We'll sometimes draw it this way and you know, just by force of habit, but oftentimes when you have 1,3-diketones, it exists in the enol form, right? And we can imagine two enol forms. Just keep things simple, I'll just draw it in one of those forms. Right? And now what we have, right, is an alpha beta unsaturated. But not only is it an alpha beta unsaturated ketone in a way, but it's sort of in conjugation with this system, right? So now if we did this, this should sort of show these two tautomeric forms of one another. Right, what we have is a very different system because this molecule, by virtue of it being alpha beta unsaturated, as well as having this conjugation all the way through to that oxygen, this molecule in many ways is electronically at the carbonyl, much like an ester as well. Does everybody see that? It's sort of like in many ways an extended ester, I guess in this case an extended carboxylic acid. Right? If we just think about so imagine we had that, right? Versus this. So here's your ester. Right? The ester has sort of conjugation through the carbonyl. This guy has conjugation through the carbonyl as well. You just have to go through that out. Everybody see that? So again, electronically it's a lot different. In addition, as what was brought up, it's also acidic. So even if you were going to try to do one of two things, right, if you were going to try to add in, you'd more likely even just deprotonate this, right, so which was the other point. So it's very acidic. So it exists in this enol form, so at the surface it's a lot less like your standard ketone, but it also is also acidic, which was the point that was initially brought up. So if it's going to add in, because it's more acidic, it's going to more likely react. It's sort of like a nucleophile reacting with something in the presence of an alcohol, right? It almost always will deprotonate the alcohol. In this case, it's even more acidic. So you're more likely to deprotonate it than anything. So, all right. So that's Claisen condensation. Dieckmann condensation is the same thing. It's just in a ring. So if we had a system like, say, for example, this ester, 1, 2, 3, 4, 5. Okay, in this case, this would be a 5-member ring. And so again, just sort of looking at the parallel up there, the products that we would generate here, right, would basically be this carbon to this carbonyl. Five-membered ring. It's got the 1,3-diketone. So using this, now you guys, from very simple starting materials, you guys could probably start to build up fairly complex terpene molecules, right? Just starting from, you could probably make, in this case it's a sort of a 5-member ring, so it might be a little bit tricky, but you guys could probably make this as a starting material. which means you can start to make ring systems. Once you make this, you can do annihilation chemistry, and so we're really able to start to build up some complexity within synthesis type problems, and so you guys should all be prepared for a synthesis problem on the next quiz. All right, I just want to discuss one more thing, and then we can do a problem if we have time. But the point that I try to make, hopefully, and it's become clear throughout the semester, at least in terms of my approach, is I think it's important that when you guys recognize the mechanisms of these reactions, where I'd like you to be, and I made this comment earlier on in the semester, where I would like you guys to be is get into a position where you can see and even predict and hypothesize, for example, that certain reactions that you've never seen before, maybe these reactions could take place. I've never seen this reaction before, but it seems to mirror reactions that I've seen in the past, and so there's a lot of features. Maybe we could do this. And so within that context, there's really a variety of reactions that you could sort of classify as enolate-like. And this is just some examples. So first of all, if you have an enolate, there's numerous electrophiles that you can imagine adding into, right? Things that we haven't discussed yet, alkyl halides, for example. You know, you guys should all figure that, oh, if I make an enolate, it's a new nucleophile, what are some of the electrophiles I've seen? Well, I've seen alkyl halides, so I think I can probably take an enolate and react it with an alkyl halide, and you'd be right. What about an epoxide, right? I should be able to take an enolate and react it with an epoxide, you'd be right. I think some others off the top of my head. Those are just two that we've sort of seen. And so you guys should all be able to do that. You know, we've seen the enolate as a nucleophile, what are some of the electrophiles, and it shouldn't be that big of an intellectual leap to simply say a lot of the chemistry and transformations we've seen are simply identify a nucleophile, identify electrophile, and consider sort of what happens. But where I want to go is just somewhere slightly different, and that's the idea here between the acidity of an alpha proton to a carbonyl. And by virtue of being able to deprotonate this, generating a new carbon-carbon bond, right, you sort of recognize that the reason you can do this deprotonation is because of this new resonance form. So, you know, to start to think about what are some other structures that I might be able to sort of use that would have similar like characteristics, you know, you might be able to predict these. So much like a ketone, one other carbon-based nucleophile might be something like this. You guys recognize what that structure is? You guys seen that before? Isn't it? This is what this is called here? Nitro. This is nitrous. This is nitromethane. Okay. And what you see in this is that the sort of nitrogen-oxygen double bond is very much like a carbon-oxygen double bond. Right? And so you might imagine, and in fact, this is even more acidic because you got this positive charge next to it. So it turns out that you can take this and treat it with a variety of different bases. pKa's of these are actually close to what we saw with the 1,3 dicarbonyls. The pK is actually somewhere around 10. So you can take a molecule like this and treat it to a base. And again, you could use something like sodium hydroxide even, or LDA, or anything else like that, and what you should be able to sort of predict is that you're going to get to a molecule that looks like that. And so you should be able to see parallels here, right? You know, I deprotonated this and pushed the electrons up into the oxygen. I've deprotonated this and pushed the electrons onto the oxygen. The only difference here is what? That we have nitrogen sort of in between. And then all of those electrophiles that we discussed with, you can imagine reacting with something like this, right? So I'll just show it with a alkyl bromide, for example. And now what we've done is we've made new nitroalkane compounds, right? Which in themselves could be valuable. So this is a nitro group. The other parallel here is that what does this nitro group also remind you of? It's kind of like an ester or a carboxylic acid. So it turns out you can also reduce these nitro groups. And so you can imagine this could be a good way to, say, for example, make amines. So again, you reduce this, for example, with hydrogen and nickel, which is fairly standard conditions that we saw under reducing additions for, say, for example, alkenes or even some carbonyls, and we can get to amines. We sort of want to show this an example, right, of chemistry that might not have seen, but that you should be able to sort of reason based upon what you guys have learned. So again, there's a parallel there with enolate chemistry, right? It should be fairly apparent. You could treat that with the numerous different electrophiles, generate new carbon-carbon bonds. And then from that nitro, again, you could do things with it. You could reduce it, make the amine. Again, a number of different things that you could do. Sure, yeah. In fact, these nitroalkanes, one of the sort of common ways, also happens to have a name. If you treat these with aldehydes, it would be very much like a aldol reaction. And after protonation, following protonation, you get to molecules like this. Now, again, from this standpoint, you could imagine you've got a sort of an amine and an oxygen, right? And this is at the same oxidation state, this is very similar now to things like amino acids, right? So amino acids are effectively, you guys learned about amino acids a bit with Guillermo, right? So amino acids, right? Usually you have a nitrogen, carbon, carbon, right? And so as you can imagine, amino acids are found in a variety of different natural products and things that have perhaps evolutionarily or otherwise been created for important physiological reasons. And so here you have a nitrogen, carbon, carbon, oxygen, and so you can imagine derivizing this in ways that might parallel perhaps how nature may derivize things like amino acids. So you can imagine oxidizing this to get to higher oxidation states at that position, or a bunch of other aspects. So anyways, I just sort of wanted to make that point, and yeah, so I think that's fairly much all that we're going to discuss for enolate chemistry. Next class, we'll begin to get into conjugated systems. So we're going to actually, then I'll start getting into homo-lumo interactions, and so we'll start to see reactions of that sort. But again, for this upcoming week of quizzes that are coming up, I want you guys to really start to, obviously you'll get questions from this week in terms of things that we've discussed, but you'll also get, synthesis, so it's important that you keep up with other materials. So, all right, so I was asked to, we got about 10 minutes left, and I was asked to put up a tricky question. Can't put me in a spot, Saif. Come up with a tricky question off the top of my head, especially when I'm battling this cold. Why don't we just do a synthesis problem? Because you guys will all have a synthesis problem on the quiz. So let's do a synthesis problem, and maybe we'll do Maybe we'll do one that involves annihilation chemistry. So. All right. So this is what we'll do. So here's the starting material that I mentioned in the Robinson annihilation. Okay. What I would like you guys to do is try to make this molecule, and I would like you to make it retrosynthesis from 2 carbons. So all the starting materials will be 2 carbons or less. So let's break this down retrosynthetically to try to come up with a synthetic strategy in which case we can make this. So the units can come from 2 carbons or 1 carbon, but let's really try to sort of break it down. Okay. So I think for a question that's sort of 2 carbons or less, one of the first questions that you may want to ask is how many carbons are in this molecule more generally. Right? And there's 7 carbons in this species. So you're not going to be able to break it down into a series of 2 carbon containing compounds. And so if there's any point at which case you could say, for example, chew off a single carbon, that may be a good time to do it. And so I guess I'm hopefully trying to prod you guys in this direction, but how might we, what might we want to be the last step in the synthesis in a way that we can sort of chew off a single carbon based upon what we've seen? I heard people, yeah.
Or
Well, I guess what I'm getting at is where's the carbon, like that we could probably get rid of or bring in at the very end?
Oh, the methyl.
Yeah, probably the methyl, right? So that might be probably the last one that we want. Does that seem like a good choice?
Yeah.
Why? And how would we do it, right? So we can start with that as the starting material, right? We can treat it with base, right? We've got a specific carbon in between that we know that we can deprotonate, right? So we know that if we treated this to a base, we would specifically go after one of these protons to generate that enolate. And then what would we do? We just treat it with what? Yeah, an alkyl iodide or methyl iodide or methyl bromide, right? So let's just say 1 base, just be more specific, I guess. NaOH, for example, followed by, anytime I do the Rubin-Owen rules, it's kind of like 2 in 1 step. Let's say iodomethane. Right, so that could be the step. So now we broke it down into sort of 2 steps. I'm sorry, we brought it down to sort of 6 carbon containing molecules, and Saif was saying maybe early on that there's a reaction that we might be able to use here that might make a lot of sense that we just saw, that might help us, get away from the rig, maybe create the rig. Yeah. Say that again? Yes, exactly, the Dieckmann condensation. And so again, the Dieckmann is a great way to make 1,3 diketones. It doesn't matter which one we choose, it's symmetric, but what happens is, you can sort of identify that nucleophile, shown right there. And so the Dieckmann would be, again, it doesn't really matter what we put here, we'll just stick a methyl group there, we're eventually going to have to get rid of that methyl group afterwards, but that shouldn't be an issue. But that would be the Dieckmann starting material. Okay. Now we're asking the 2 carbons or less. Okay. The benefit is 3 carbons or less. All right, sake of time, let's change the rules real quick and say 3 carbons or less. Because we really don't have much time, and I think there's a very obvious transformation here, and it would be starting with acetone, and I think of any starting material, acetone is probably as good as any to start with. So, knowing what I know about sort of price of chemicals, we can go with 3 carbons here. So There's a very easy disconnection here that can break this down that you guys should be able to see as we discuss that. Anybody see it? Yeah,
You could do a Michael
exactly.
between acetone and
Right.
yeah.
Right. So this would be acetone. Right? And again, given the time, we could break our 3 component guys down to 2 fairly, we could do that on our own time, but. Okay, if we have time, we'll break it down to 2. But yeah, so now acetone is down to 3. This guy's 1, 2, 3, but we have the 4th, but that should be fairly easy, right? How do we just want to get rid of one of the methyl groups, and this one would be probably the easiest one to get rid of. So how might we make this from something that has 3 carbons or less? Probably just do a transesterification, right? Or even an acid chloride or something. Yeah, there we go. Chloride. All right. And that would break it down to 3 carbons. So we've got a couple minutes left, so I guess we could try to go back to our initial things. But again, this is all cheap stuff. This is commercially available. Actually, this is commercially available as well. This is commercially available. But if we wanted to break this down, each of these down to 2 carbons or less, we should be able to do that as well, right? Making acetone from 2 carbons or less should be fairly straightforward, right? We just got to figure out a way that we could, say, for example, make one of those bonds, right? So how do we do that? Say again? Yeah, so we take it, we probably go with the Grignard. The challenge is that a Grignard, we'd have to probably do like a 2-step reaction, right? Because the Grignard, we'd want the Grignard to probably come from the aldehyde. Because what would happen if we tried to go to the ester, for example? We'd get double addition, right? That would be the issue. So you probably want to go from the aldehyde, which would mean the first step is this. And the second step would be what? We just want to oxidize back up, right? Because once we add in, we'll generate the alcohol, and then we'll probably want to oxidize back up with ACC. We can also go directly with something like a Gilman reagent and an acid chloride. Would be another option that we could do. So there's lots of options here. Again, in this case, it would come from a carboxylic acid, right? You make acid chlorides from carboxylic acids. Right? Using thionyl chloride. And how do we make carboxylic acids? You can oxidize it up, but that doesn't really help us with the carbon count. Is there a quick way that we can make this from 2 carbons or less? And I'm specifically thinking about this bond right here. Is there a way that we can make that? We take vinyl lithium, and we want to make acrylic acid. We take vinyl lithium, and we treat it with what? Sure, there's other ways to do it as well, but how would we do that transformation? What's the electrophile that we use to make carboxylic acids? In the air. Carbon dioxide. Take that treat with carbon dioxide. That's how we get the carboxylic acid. So again, breaking it down to 2 carbons isn't that difficult. The reason why I switched to 3 was in part because I think there was better disconnections, specifically the Michael addition, which simplified things a lot. Okay? All right, so quiz next week. I'm having a little bit of luck with the, I don't want to jinx myself, but I am having a run of luck with the video, so hopefully we'll